Mi zittisce tutto il tempo. Hey, okay. Now we are live. Come back soon here in sunny days of Napoli. Here, the second day of our beautiful NapulETH. So back in the days, and be serious today, guys. Today we have another speech, super interesting, with a developer, we can say that, okay? And you say that Ethereum doesn't need more Solidity devs, it needs all devs. That's right. So these are the words of Ovidiu, Damian, and come on the stage and talk about the P squared and why this question.
So, as people will see during my presentation, we started with. Okay, cool. So we went with wanting to bring multiple programming languages on Ethereum, specifically because there's actually, if you look on the data, there's so few Solidity developers actually in the world. It's a programming language that is currently used solely for making EVM smart contracts. Basically, if you do not care about blockchain and at some point start caring about blockchain, it's simply something that will stop you from getting quicker into developing anything that's smart contracts, just because the programming language is not used for anything else. And we thought that instead of having multiple users learn Solidity, we can do something using our expertise in order to enable developers that don't know and don't care about Solidity to develop on Ethereum and other EVM chains. So let's get into it. So one of the main reasons for which we wanted to solve this is because this brings basically the fact that EVM is so centered around Solidity is creating lots of fragmentation. This fragmentation can be represented in many ways. First of all, we have fragmentation of developers, as I've said before. There's many developers that don't know Solidity. It's hard to learn it initially, and they know other programming language and would rather just code in that programming language. And we all know that developers can be a little stubborn sometimes, so yeah. Second of all, we have fragmentation between EVM and chains that are not EVM. For example, if I'm a good Solana developer, that doesn't make me a good EVM developer because it's a completely different paradigm, it's a completely different programming language, Rust is very different from Solidity and so on. Moreover, another ecosystem that's very different. If I'm a good Sui developer, I have to learn Move, I have to basically, then if I want to get into Ethereum, I have to learn Solidity and so on. It's basically so many hurdles if I want to just be a Web3 developer. It shouldn't be so complicated to say so. Moreover, having this type of fragmentation of builders and developers creates fragmentation of liquidity. People are developing on different ecosystems, and it makes it hard to have all the crypto liquidity accessible for everybody, which would bring obvious great benefits. So, our solution to Web3 fragmentation is verifiability. And what I mean by this, we as a company have lots of experts that are basically amazing when it comes to formal semantics. Formal semantics is the science of creating programming languages and defining them in a mathematical way, to say so. And because we are good and passionate with blockchains and formal semantics, we thought we would make them kiss, in the sense that we could bring formal semantics to blockchain and do something with on-chain formal semantics, which is the way in which we are going to help with this. And here comes verifiability. If you are able to mathematically define a programming language, you are able to generate mathematical proofs that some code results in something specific, which can also be done for on-chain code. Now, the solution we are proposing is first of all, universal in terms of programming languages and program execution. Basically, whenever you start learning a blockchain, you wouldn't need to learn a specific programming language. You could code on any chain using any programming language as long as it's adopting our tech in any way. Second of all, it's universal in proof mechanisms in the sense that we have tested whether our mathematical proofs generated, whether our mathematical proofs that are generated with formal semantics are checkable easily with mainstream ZK circuits, and they are. Basically, we've tested everything there is on the market, and it's mainstream for ZK, and it worked. And it's universal in the sense of distributed consensus security guarantees. Or in not so complicated language, it's very much compatible with blockchains in the sense that it's not hard to get to a validator consensus regarding the fact that it's secure. Now, in order to do that, we have 3 products, to say so. First of all, the verifiable language machine, which allows one to write smart contracts in any language. It even allows people to basically define new programming languages and use those. Currently, we have a demo, which I'll show at the end of my presentation, which allows you to, on the same blockchain, it allows you to write smart contracts in Solidity, EVM, WASM, and Rust. Why did I put Solidity and EVM and WASM and Rust in different languages? Because we support running Solidity directly without compiling it to EVM and Rust directly without compiling it to WASM, just to show that it's possible to execute high-level programming languages as well as low-level programming languages. We have the verifiable settlement layer, which allows you to generate proofs of execution and settle them on a common layer across ecosystems. Basically, you could run your own programming language or smart contract in your own language on our VLM and then send proof of execution to Ethereum, let's say, or Solana or anything like that, to have mathematical proof on chain that that code has been executed and has resulted in something specific. For example, let's say I want to execute 2 + 2 is 4 in Python. That's not possible in EVM, but it's possible on our VLM. You execute it, and using VSL, you can check that that code has actually, that 2 + 2 is actually 4 in Python, and have that proof on chain on any blockchain, and check it with any ZK VM using our VSL. And the verifiable consensus protocol is what keeps the VLM and VSL decentralized. We can't censor it. We can make huge changes to it. We can basically say, no, this is code that can't be executed anymore or anything like that, because we have validators and a specific consensus protocol, like other chains, which basically keeps security in check. So for the VLM, basically, this would help bring, in an ideal world, this would help bring 38 million developers to the current Web3 ecosystem, because people that know Python, TypeScript, Java, or even that know how to write code by doing vibe coding via AI prompts can now basically come to Web3. The VSL would basically help over 100K Web3 apps that are in existence today to basically settle their own on-chain claims quickly and securely. And the VCP in this case would help process billions of transactions concurrently. Now, let's explain a bit better what's the market for us in the sense of bringing more developers. So according to a study made in July 2024 by Electric Capital, there's only 8.8K active Solidity developers in the world, which is wild. That's wild. It's wild when you understand that it's so few of us. And if we go a bit further, we understand that there's just 26K Web3 developers in the world that are active. Of course, if you have coded one smart contract in your whole life, that doesn't make you a full-fledged developer, but just 26K developers. This is why maybe if you ever tried building your own project, you saw that developers are so expensive in Web3. So basically, by using our tech, you get access to 26 more million developers by just enabling C, Python, and Rust. You can get access to even more Web2 developers by basically supporting other mainstream programming languages like TypeScript, Java, and so it's JavaScript, and so on. And in 2030, when we will have prompt engineers as a more clear pathway for developing, you will also be able to have access to even more developers by simply basically allowing prompt engineers to write and settle code on chain. Now, to go further on this, instead, people generally don't think about verifiability until it's too late. Instead of asking, okay, why should my code be verifiable? We want to change this paradigm into why not yet. So there are obvious reasons for which your code should be verifiable. And one of the first reasons is to prove that the code executed is actually what people believe it is. So on-chain, it's relevant if I have gotten to my end result by executing 2 plus 2. Sure, I got the result 4, but I can get to the result 4 by executing 3 plus 1. If my code is verifiable and if execution in general gets verifiable, we can keep in check and we can check validators and compilers and so on and make sure that they function as needed. One cute story regarding this is the fact that someone from our company at some point, using formal semantics, helped audit the GCC compiler. Some of you might know the GCC compiler. It's basically the most widely used C++ compiler, and it's like huge in the sense that that compiler is basically, how should I say it? That compiler is one of the most well-maintained and complex open source projects there is. And after they created the formal semantics of that in order to test the compiler, they have run all the tests to test that compiler, and using those formal semantics, they have actually found some bugs in the compiler. Obviously, in the meanwhile, they have also found some of their little mistakes. Okay, maybe we didn't understand the C++ programming language as well as we thought, and they found one of their own mistakes. But the point is, just by defining C++ as a mathematical model and running the usual tests of a compiler against those tests, we were able to find bugs in one of the most well-respected compilers on the planet. Now, let's explain how exactly this helps not just developers themselves, but also infrastructure providers. So whenever you want to add a language to your chain, so let's say that tomorrow Vitalik decides, okay, from now on, Ethereum will try to support Rust as well, besides Solidity. They will have to have a code interpreter. They will have to create a compiler that compiles that to WASMs or even to EVM or anything like that. They will need a symbolic executor, a model checker, a program verifier. That's huge work for anyone that wants to offer code execution in a secure way. That's a lot of work, and it has to be repeated from zero for each programming language. This is why most blockchains only support execution of only one programming language. And this is where we come in. Instead of having to build these tools for all of these languages, we use a framework called K, which is a framework that was initially developed by our CEO while he was working at NASA. But in the meanwhile, he started his own company, which is Pi Squared. And this framework, K, basically is the framework that allows you to easily define your own programming languages in a mathematical way. And based on that, so based on your definition, so you only write one mathematical definition, and using that mathematical definition, you can then automatically generate an interpreter, a compiler, an executor, a checker, a verifier for that programming language. So you write one thing and then generate everything based on that. It's way more automatic, it's way more secure, it helps find bugs even in well-known open source language projects and so on. So let's see an example. This is how a simple programming language looks like when defined in the K framework. So if this looks complicated to you, I promise that it's not. And you don't, so you have to somehow trust me, but to explain this, just so you know, this is basically the first rule, the first lesson that students are taught at the university when learning K. Basically, where our CEO is a professor in Illinois, Champaign, nearby Chicago. Whenever he has the first lab with his students, this is the first thing they learn. So after 2 hours of learning K, they can write this themselves, understand it, and run code themselves using a made-up programming language called Simple. Sure, you can't expect that language after 2 hours of student work to have the same capabilities and speed of C++ or Rust, but the point is they can create their own programming language, they can add it on chain, and once that is done, after just one lab, that can generate interpreters, compilers, and so on. Now, how does this actually bring programming languages on Ethereum or on other chains? So in an ideal world, we would sit Vitalik down, or we would sit someone else from other chains down and say, hey, why don't you change all your validators so instead of executing code directly, they use formal semantics to execute their code? In that ideal world, he would say, yeah, that sounds cool, and do it. But that's unrealistic. That won't realistically happen anytime soon because validators want to keep it safe, and so on. So the more realistic way of doing it is by us having, let's say, our own chain. Think of it like a layer 0 or a layer 2, or however you want to call it, which does work based on formal semantics. Whenever you want to run some Python code or some Rust code or anything, as I said, you want to write 2 + 2 is 4. You run it on our chain, and after you run it on our chain, you also get the mathematical proof that that code has been executed and it has gotten to that result, 4. Now, because mathematical proofs are generally huge in terms of blockchain storage, like a mathematical proof can occupy a few megabytes of data, which is a lot for blockchain. What we do is we then take that mathematical proof and put it into a ZK proof so that you can easily store it on chain. And then, obviously, with a data availability layer and with ZK VM, check it quickly on other chains to make the result available. You basically can come on Ethereum, ask, hey, I want to execute 2 + 2 is 4 in Python. We listen to that, we execute the code, and you get the result back on Ethereum. Let's see how the workflow is exactly. So basically, you define your own programming language. Then, based on that, you can generate an interpreter, and that interpreter can run the program. Of course, it has an execution environment and runs the program, has those hints, those proof hints, is able to generate the proof, and based on the math proof, it can then get to become a ZK proof. Now, let me check how much time do I have. Okay, I think we're good with time. So what I want to do now, because I've talked a lot theoretically, I want to show you a quick video, and I will explain while it's going with how that actually works. And let's get to it. So basically, we have the bring your own language demo, which is a chain which have modified to support multiple programming languages. It's an EVM compatible chain. We have basically modified we have modified the execution engine of Rust Ethereum, and we have made it so you have a language registry. Basically, this shows all the programming languages that are supported on our chain. Initially, because the chain was just spawned in the video, we only see EVM supported. Each chain has their own ID, pretty much like an address for smart contracts. And that ID is a unique identifier that is then used by nodes to identify those languages. And obviously, each language will have their own hash, which is basically something that can be used to check that the code expected to be used is actually correct there. Now here I was showing basically the hash, and we can also check the contents of said code, which I'm doing here. Basically, this is a mathematical definition of Ethereum. It's very long. I'm not going to go through all of it in the video, but basically, using this, you can run Ethereum code, which we actually do in the video, and you'll see. So, as we get back here, we go to the next tab, and we try to add a new programming language. Okay, so I'm choosing from my list of already made languages that I've prepared for the demo, and I'm adding Solidity directly. You can see the definition of the language I'm adding, and you can see I'm signing a transaction, and I'm simply adding the new language. Transaction completed successfully. There we go. Now Solidity is also available on-chain to run directly. So no compiling to EVM, running Solidity directly. Now I take the ID and put it there because I want to deploy a contract. And I need to tell the node, hey, the contract I'm trying to deploy is in this programming language, so that the node knows how to run that code. And I'm adding the contract. As you can see, it's a typical USDC contract in Solidity, typical ERC20. You can see MetaMask is even detected that this is a contract deployment. And it's nothing special. Basically, it feels like classical EVM. It's just that you can use lots of programming languages on it. Okay, we have the address of the contract I deployed. I'm copying it, and we can now go and interact with said contract. Okay, I'm going to input the ABI of said contract to interact easily with it, of course. And there we go. I'll choose USDC, and now I can load a contract. You can see name is detected, symbol is detected. I'm going to copy my address and check my balance. Obviously 0. The contract was just deployed, so my balance is 0. I'll mint some tokens. And a simple transaction request. Nothing too special. And it's okay for it to not feel special. Using multiple programming languages should give the same seamless experience as using general Ethereum. We have a transaction receipt, as usual, like in Ethereum. And we have just executed code, and I have minted tokens. Now I can check my balance again. And there it is. I have my tokens. Now, what we're going to do during the demo is also check this in Explorer. You can see that our fork of the Explorer also sees and understands that this code is written in Solidity. And basically you can see that I have some transactions that are in Solidity. And this is where the magic comes in. The first few bytes that you see there are the only thing that's different from classical EVM, because the first 4 bytes in each contract is actually the language ID. So the validator basically looks at the first 4 bytes, knows, okay, this is this programming language that I have to run. Let me run this code in the programming language of the ID you provided. Now, I'm going to add a new language. I'm going to add Rust. We add it real quick. And this transaction was completed. It's available on chain. And I can deploy a contract in Rust, of course. You can see that's actual Rust code. And there we go. We have wrapped Bitcoin implemented in Rust and so on. It's basically kind of a ERC20 copy of a contract, but written in Rust. I'm going to allow myself to spend my own tokens to basically show that, just to show that it's working. MetaMask even detected it as a spending cap request because me as a caller of a contract, I don't care in what language you've written your contract. As long as it returns what it should, that's all good. Got my token allowance. I can also show on chain that this is a Rust contract. It's viewable on chain. It's working all good. I can also see the first 4 bytes for the Rust token ID, for the Rust language ID. You can see 72757374, which is the ID of Rust. And before going further, I'm also deploying an EVM contract to show that classical EVM also works. We're on an EVM compatible chain. That, as you can see, that's EVM bytecode. And there we go. Transaction will be completed soon. We copy my addresses again. I'm checking my balance again. All works well. I'm going to deposit some Ethereum to get back some wrapped Ethereum because that's the contract I've deployed. And as you know, if you want wrapped Ethereum, you have to deposit Ethereum. All good. We have the transaction receipt. Everything works well. Everything is nice. Okay. You can see the contract now has 0.1 Ethereum balance because I've sent it some. My balance has been depleted. And you can also see it knows it's an EVM contract. And it has a balance of 0.1 ETH because I've sent it some ETH. And you can see that basically is detected as a token transfer here. And now, what we can also show is the fact that WASM can also be added on chain. Basically, you can execute Rust or WASM directly. But we're going to go a bit faster through these to save time because it's similar to the other programming language. So we have WASM. We're deploying a Doge contract in WASM, which is, again, bytecode. Okay, done. We interact with it real quick. Again, copying my address, checking my balance, minting some tokens. And as this is done, I should be able to check my balance. Okay, done. Balance is there. All works well. No fuss. You can see it's a WASM contract. Its token name is detected as being Dogecoin. All good. Okay. And the last language we're showing that we're supporting for the demo is the programming language called Simple, which you have seen before in the presentation. It's that programming language that usually students are coding after one lab. that's to also show that you can invent your own programming language and come with them. It doesn't have to be something mainstream. It can be whatever you want. So we have the simple programming language. That's literally the name. Okay, we have added it real quick, and we can, again, go through the same flow of deploying. And let's say we're deploying the pi squared token in simple. Contract is deployed real quick. Once that's done, we're gonna mint some balance and all will be well. There we go, minting. Minting 9.86 tokens, which is pi squared. Okay, result is there. We have 9.86 pi squared tokens. And it's also detected as the programming language being simple. We also have the bytes there. All's fine. So this has been the Bring Your Own Language demo. And before we end, I've got one more short demo to show how everything works. So we have shown different programming languages working on the same chain. Now, what I want to show is, Now what I want to show is multiple programming languages interacting with each other. Like, we can have a DEX in which one token is written in Rust and another in Solidity, and it will work seamlessly. The tokens themselves don't know they are written in different programming languages. They just are. They can communicate seamlessly without any issue. We have multiple tokens. We have a router contract, which is written in EVM. You can see again the bytes. Then we have the pi square token written in simple. We have the wrapped Bitcoin in Rust. We have a DAI token written in EVM, USDC in Solidity, and Dogecoin in WASM. And if I try to do a swap, let's say I'm swapping 986 USDC into Doge. I'm doing a swap real quick. Of course, first I have to allow the spending of the tokens. As it gets confirmed, I will be able to actually do the swap. We wait a bit for the transaction to go through. And now I also get a transaction request, which I'm confirming. And the transaction was executed. You can see the balances have changed. And yeah, that's pretty much as simple as it gets. You can simply have multiple programming languages interacting with each other. You can basically see I have interacted with an EVM contract which called a Solidity contract that interacted further and done a swap with a WASM contract. So yeah, that's basically as easy as it gets to have multiple programming languages working together on the same chain in a decentralized exchange in this example. So now, as I've shown you all this, and we're getting to the end, feel free to follow us on X to stay up to date with everything we're developing. And you can also go to our developer portal to try out what I've just shown you for yourselves. We just had a month of DevNet that has ended recently, in which we've collected feedback for our products from users, and we'll closely get to a testnet. Now, before I end, do I also have time for Q&A? Yeah. Yeah. Well, no, it's a transaction on our DevNet. The prices are not necessarily real. It's basically we have just named the tokens to have relevant names, but we didn't actually go on the DevNet and say, okay, let's track the real prices. The point was to show that multiple programming languages can work together. But in real life, if we launch it in this, basically, I think 1 hour later after we launch it, we'd probably have arbitrage boss that would keep our price like in reality. So if that's all, thank you, everybody. Good. Thank you, everyone.